Welcome back to part 2 of our podcast on neuromorphic computing. Let's continue with, are there specific companies or actual technologies leading the charge here?
Oh, absolutely. Intel's low-heat chip is a really prominent example. They put a lot of emphasis on its self-learning capabilities.
Okay.
Then you have IBM's True North. It really demonstrated the potential scale of a computer chip, simulating over 1 million neurons on one chip.
1 million neurons. Wow. Old, but still impressive.
Yeah, showed what was possible. And importantly, there's BrainChip's Akita processor.
Akita?
Yeah, Akita. It's actually a commercially available neuromorphic processor.
So you can actually buy it now.
Absolutely, which really indicates this tech is moving beyond just the research labs and into practical applications that could eventually reach the public.
So it's not just some far off sci fi concept. There's actual hardware being built and even sold.
Exactly. And what's really fascinating here, I think, is the relationship between AI and neuroscience. It's not just AI borrowing from the brain.
It goes both ways.
It really does. Studying the brain is obviously driving advances in AI, especially neuromorphic computing. But at the same time, the models and the architectures being developed in AI, they're actually giving neuroscientists new tools, new ways to understand how the brain itself works. And
So it's like a feedback loop between the two fields.
yes, it's a really compelling synergy.
Okay, but like with any new tech, it can't all be smooth sailing. There must be challenges, right? Limitations. What's holding neuromorphic computing back from being everywhere right now?
You're absolutely right to ask that. One really significant hurdle is simply programming these new types of chips.
It's hard to write software for them.
Yeah, the traditional tools and methods don't really apply directly. We need to develop entirely new ways of thinking about programming new tools specifically for this kind of hardware.
So it's not just learning a new language, it's like learning a whole new way to instruct a computer.
Pretty much. It's a steep learning curve for developers, for sure.
Okay, that makes sense. What else?
Another thing is the limited adoption so far because it's still relatively new.
Right.
There isn't much standardization between the different platforms and different chips.
So code written for Intel's chip might not work on brain chips.
Yeah, that lack of standardization makes it harder for developers and can slow down wider use. It makes it challenging for you as a potential user or developer to know which horse to bet on, so to speak.
Okay. Difficulty, programming, lack of standardization. Anything else?
Well, neuromorphic computing is still in the early stages of development.
So it's not replacing the chip in my laptop tomorrow?
Tomorrow, no. It's still got a way to go before it's mainstream for everyday devices. But the potential is definitely there.
Right. So there is huge potential down the road. So what does that future landscape potentially look like? How might this impact you and the devices around you in, say, 5 or 10 years?
Oh, the potential is genuinely exciting. I mean, we can really envision AI moving much more to the edge.
From the cloud onto the devices themselves.
Exactly, enabling more localized, more immediate processing in just a huge array of devices you'll interact with every single day.
Like what kind of things?
Well, this could really drive the advancement of smart cities. For one, think about traffic management, energy grids. It could lead to breakthroughs in medical diagnostics, maybe sensors that can detect health issues earlier, right on your body that could directly benefit your health.
Wow.
And just generally a huge proliferation of low-power AI applications in almost every part of your life. Smart homes, wearables, and appliances.
So a more responsive, maybe more personalized tech environment all around us.
That's the vision, yeah. And looking even further out, this is maybe more speculative. There's this really intriguing idea of potentially combining neuromorphic computing with quantum computing.
Whoa, neuromorphic and quantum.
Yeah, quantum AI. The combination could potentially unlock capabilities we can barely even imagine right now. It could revolutionize fields like medicine, discovery, and material science, really for the benefit of everyone.
Quantum and neuromorphic. Okay, that's definitely something to chew on. So let's bring it back down to earth a bit for our listeners right now. What are the key takeaways, the main advantages of this neuromorphic approach that you should really understand?
Okay, yeah, good idea. Well, first and foremost, I'd say it's the ultra low power consumption.
The energy efficiency.
Exactly. That efficiency is just critical for the world we live in now with all the mobile devices, IoT, gadgets, edge AI, things that you rely on constantly.
Okay, low power. Got it. What else?
Then there's the faster real-time processing.
Things happen instantly, pretty much.
Imagine robots, self-driving cars, industrial automation, responding almost instantaneously with minimal delay. That speed could be absolutely critical in safety situations that directly impact your well-being.
Right. Responsiveness is key there.
Absolutely. Then we also have the adaptive learning and self-organization, the on-chip learning we talked about. These systems can keep learning, keep adapting to new situations as they happen without needing constant retraining from the cloud. This makes them much more aware of the context and the environments you actually live and work in.
Okay. And they're good at spotting patterns.
Extremely good. Their efficient pattern recognition capabilities will likely have a huge impact. Think speech recognition on your phone, image processing, and motion detection for your home security. Even potentially big advancements in healthcare diagnostics, like spotting subtle signs of disease in scans much earlier. Basically, better at seeing and understanding the world around them, which benefits all of us.
That makes sense. More capable devices.
Precisely. And the brain, like architecture itself, that's a benefit too, because it's aligned more closely with how biological intelligence works.
Right.
It could potentially lead to AI that feels more intuitive, maybe more human eventually, perhaps even with better cognitive abilities or down the line, some form of emotional understanding that could really change how you interact with technology.
More natural interactions, maybe.
Hopefully. And don't forget the on-digit intelligence, the edge AI aspect.
Right. The privacy angle.
Big advantages there for data privacy. Plus, less dependence on having a constant, strong network connection for the devices you use. Faster local decisions without sending your personal info off somewhere else.
Less reliance on the cloud. More control locally.
That's the idea. And remember, these systems are also designed to be scalable and fault tolerant.
Robust and resilient.
Yeah. Good for critical applications, space exploration and military uses, things that contribute to global security and advancement, where failure isn't really an option.
Okay.
Well, perhaps most excitingly, many believe it opens the door to the next generation of AI. It might be a key step on the path towards artificial general intelligence, AGI.
Machines that can learn and reason more like humans.
Exactly. More intuitive, human-like machines, which would ultimately impact all the tools and technologies available to you in the future.
So yeah, neuromorphic computing really isn't just a small tweak. It sounds like a truly fundamental shift in how we're trying to build intelligent machines.
That's absolutely right.
Drawing inspiration directly from, well, the most complex and efficient computer we know, the human brain itself.
That really is the core message for your listeners. It's a significant brain-ensplazered step forward for AI.
Yeah.
And as we keep building machines that operate more like our own minds, the potential is there to create tech that's not just more powerful, but maybe more intuitive and hopefully, as some of the research suggests, maybe more human-friendly in how it interacts with you.
It definitely makes you think, doesn't it, how this whole brain and split approach might completely reshape the future of technology and how we as humans interact with it all. Thanks for exploring this deep dive with us today.
Thanks for joining us on Technically You. Like, follow, and share this episode with someone who loves tech. Until next time, stay curious and stay connected.